Very good. So we conclude our morning session of this Wednesday on amplitudes with Freddy Cachazo from the Perimeter Institute. It's a pleasure to have him talk to us about generalized Feynman diagrams and tropical Grassmannians. Welcome, Freddy.
Okay, so thank you very much. And then, of course, let me join my voice to all the speakers in thanking the organizers and especially Nastia for helping us get virtually together. And of course, it's not such a great idea to be the speaker that is standing between you and lunch. So I'll try to do my best to stay within the time slot. So let me start by thanking my collaborators. These are a group of excellent masters and graduate students. And of course, our team's mathematician, Nick Erwin. So let me start by giving you the outline. So I'm gonna start by boring you, or hopefully not, defining boring 3-level phi-cube Feynman diagrams, but with the idea of connecting them to something that is called the tropical Grassmannian G2N. And then showing how the tropical Grassmannian can be generalized to other Grassmannians, and that will lead us to the idea that maybe Feynman diagrams can also be generalized. Of course, we know a dual formulation of Feynman diagrams, which is given by the CH5 formulation of points on CP1. And therefore, we will conclude that there is also a natural generalization of CHY to higher projective spaces. And as you can hear, James had problems with his computer, and I might have problems with my voice, but let's see how far mine can go. At the end, I'll conclude with a powerful simplification, which is assuming now that we have planarity for Feynman diagrams. In terms of the Grassmannians, we will have total positivity, and for CHY is restricting to integrants, which are part Taylor-like integrants. So the goals for this talk are very simple. One of them is to try and convince you that standard scattering amplitudes are the simplest example of a large mathematical structure in which Feynman diagrams are generalized to arrays of Feynman diagrams, interconnected in fascinating ways. And the second one is to show that exploring the full hierarchy of objects reveals that properties that we take for granted in standard amplitudes are quite special and almost coincidental. So 2 examples that are very obvious is that all 3-level Feynman diagrams are planar with respect to some order. And the second one is that the number of planar poles is n times n minus 3 over 2, which happens to be the number of independent kinematic invariants. So let's start. So of course, we're at an amplitudes conference. So telling you about 3-level Feynman diagrams for phi-cube theory without any flavor structure would be extremely boring for you. So I'm gonna try a different approach. I'm gonna try to explain it to you as I would explain it to a mathematician. I would say that Feynman diagrams are given by rational functions as something that we call kinematic invariants. And the kinematic invariants are arranged in a symmetric matrix that has 0 elements in the diagonal and whose rows and columns are up to 0. We construct the rational function using propagators, and there is one propagator for each way of splitting n or partitioning n into 2 subsets, each of them with more than 1 element. For each such partition, we define a function that is given by summing over all the SAs with labels in A or labels in B, given this condition of momentum conservation, that's how we call it. These 2 objects are the same. Now we can count how many possible propagators we have, and it's very easy to see there is 2 to the power n minus 1 minus n minus 1. Now, we construct the rational function by multiplying such propagators, and they can be multiplied if any one of these conditions is satisfied. So I'll leave you as an exercise for you. It's lots of fun to see that this is precisely the conditions that in physics we use to construct Feynman diagrams. Now, the full Feynman diagram is constructed by multiplying the maximum number of possible propagators that satisfy these kind of conditions. And it turns out that there are exactly n minus 3. So for 6 points, we have 3 propagators. So this is an example. And in total, the number of total possibilities of Feynman diagrams is 2n minus 5 over factorial. Now, after you're done with this beautiful explanation to a mathematician, they would say, well, but wait a minute, I have seen that. We have a structure that is identical to that. It's a simplicial fan that we call the tropical Grassmannian G2M. It has precisely this number of vertices, also in correspondence with partitions of n elements into 2 sets, and edges connecting two vertices every time one of these conditions is satisfied. Moreover, they would say that they have 2n minus 5 double factorial facets, this object. These are the maximal dimensional faces, and they are made out of n minus 3 vertices. Immediately you say, well, it's amazing that there is such a correspondence between these two objects, but could just be a combinatorial coincidence, or there is something deeper than that. Well, the only way to find out is to study examples. So let's do, well, at least that's the way physicists do it. So we start with 4 points, and the standard picture for the tropical Grassmannian is just 3 points, which would relate to the 3 poles or the 3 Feynman diagrams. In this case, the two numbers coincide. But for 5 points, we get the Petersen graph, which is much more interesting. And we see that we have 10 vertices corresponding to the 10 possible propagators and 15 edges corresponding to the 15 possible Feynman diagrams. But we want something more than that, because we want to make the correspondence even more precise. So let's go back to 4 points. Actually, when I drew just these 3 points, it was a simplified version. The space that we are interested in is not just these 3 points, but the full space, which is called the VHV space of phylogenetic trees. And if you want, after the talk, I can tell you much more about phylogenetics. But for the time being, let me just tell you that the full space we're interested in is actually a collection of quadrants. In this case, it's just a collection of semi-rays joined at the origin, and each semi-ray parameterizes the length of the internal propagators in these diagrams, or the internal diagrams, the internal edges in these trees. That's why they are called metric trees. So we see that these 3 rays are connected at the point where the 3 diagrams degenerate to a quartic diagram. Now let's do something much more interesting. Let's go to 5 points. Now for 5 points, drawing the whole space would be a nightmare. So I just chose to draw a particular selection here in red on this side. So this is the full space. So we have the union of quadrants. This time, these are 2-dimensional quadrants. And the part that I've chosen to draw here for you is not any random one. It's one of the possible choices for the positive Grassmannian. So in fact, this picture of the Petersen graph and the 3 points that you saw before for n equals 4 is what is called the link at the origin. So it's a simplified version where you remove the part of the, is some sort of the projective version of the space. So to each one of these quadrants, what we have is an associated Feynman diagram or an associated metric tree. So at each point in the quadrant, we have a tree with particular lengths for the internal edges. So we see here, as I said, I chose precisely 5 of them that correspond to the planar ones. So we have the 5 planar diagrams. Now, how do we go from metric trees to evaluating amplitudes? So one possibility is to take inspiration from Baer and Crossover and say that we're going to define a quantum field theory on each one of these Feynman diagrams and integrate, say, over the space of metrics on this Feynman diagram, some quantum field theory with vertex operators and a very simple action. It's a very standard computation to end up with just the integral over the 2 lengths, L1 and L2, times an exponential of the 2.1 dimensional Green's function, which turns out to be nothing but the distance between A and B. In this particular context, we have to generalize a little bit the usual notion, because we also have to allow the length of the edges to enter, and the vertex operators are actually inserted at the leaves. Now, after having done that, we end up with a formula like this for the value of the Feynman diagram associated to this point, where DAB is again the distance from any leaf to any other leaf. Now, such distances are made by the lengths of the external propagators or the external legs attached to those leaves, plus the length of the internal ones. But it turns out that these ones drop out completely. So where you insert the external guys is completely irrelevant along the edges. Now, evaluating this for this diagram is fairly simple, and this is what you get, and this integral turns out to be the standard value for the Feynman diagram that we usually give. Now you can forget about everything that I told you, if you wish, and think that this space is nothing but the space of Schrödinger parameters. Now, We have been talking about the tropical Grassmannian, and we heard from James a nice introduction, so I can be very brief here. But let me just give you my version of how I think about tropical geometry and tropical Grassmannians in particular. So this is my little example, like the one that James had. You take a polynomial, you tropicalize it by replacing multiplication by addition and addition by the minimum operation. So this polynomial tropicalizes to this object, which is nothing but a piecewise linear function, which I have drawn here. Now, a tropical variety is supposed to be the tropicalization of the algebraic variety obtained by saying that the polynomial is equal to 0. But in tropical geometry, that doesn't make any sense. So what we define as a tropical variety is instead the set of points where the tropical polynomial attains a minimum at least twice. So in this particular case, it's at the point -1 and 2. Now, how do we tropicalize the Grassmannian? Well, we write the Grassmannian as an algebraic variety, and we take the defining polynomials, tropicalize them, take the corresponding tropical variety, and you have your tropical Grassmannian. Now, the important observation for us is the following, that tropical Plucker vectors define metrics on trees. So in other words, the tropical Plucker vectors is exactly the metrics of distances from leaf A to leaf B in a tree. And precisely the tropical Plucker relations are the conditions for such a thing to define a metric tree, and vice versa. Now, I hope you're all asking the obvious question at this point, which is that if the tropical G2N Grassmannian builds all the standard Feynman diagrams, then do tropical 3N and 4N build new kinds of Feynman diagrams? Well, that brings us back to our outline. So we have defined this connection and ask the relevant question. But before we go down in this direction, let's move to the CH5 formulation, where we can get perhaps some insights. Now, the CH5 formulation starts with the scattering equations, which connect the space of kinematic invariance for the scattering of M particles to the moduli space of M puncture spheres. And this proceeds by the definition of a Morse function on that moduli space. And the scattering equations are nothing but the conditions for finding the critical points of such a Morse function. Now, this is one of the formulas that by now we know very well, which is the construction of the bi-adjoint UN cross UN tilde amplitude, which is also a scalar, cubic scalar theory. And we have an integral over the moduli space localized to the critical points of the Morse function, multiplied by an integrand built out of part-Taylor amplitudes, or part-Taylor factors. All right, so now the math question is, if an integral over the space of configurations of M points on CP1 is connected to the tropical G2N Grassmannian, then could it be that the integral over configuration spaces of M points on higher dimensional projective spaces also correspond to higher dimensional tropical Grassmannians? And the answer is yes. In fact, it's extremely simple to just generalize the story from CP1 to say CP2. Now the space of kinematic invariance ends up satisfying what we told our friend the mathematician by simply requiring the function f to be well-defined on the moduli space, meaning it has to be invariant under the automorphism group of CP1, which is SL2C. For CP2, the automorphism group is SL3C, and therefore, the only conditions we get for the generalized kinematic invariance are then these ones that you see here. And in general, we can go to any k to CPK minus 1 and find that the space of kinematic invariance is also generalized, and these are the conditions to be SLK invariant, for the Morse function to be SLK invariant. Now, the integrand, in order to generalize the bi-adjoint scalar amplitudes, is nothing more but the natural generalization. We take two orderings alpha and beta, and we multiply the two corresponding part-Taylor factors with an integral over the moduli space subject to the condition of localizing to the critical points of the Morse function. Let me give you the first non-trivial example, which is the case on CP2 or k equals 3 and 6 points. Now you can evaluate the CH5 integral and find that the answer is given in terms of 48 terms and contains 16 different planar propagators. So what are the propagators? Well, the propagators are the natural generalizations, say, of the SABs to 3-index object and of the TABC that we usually write for standard kinematics to something that has now 4 indices. But we also find new kinds of propagators. Now, recall some of the facts I mentioned that we usually take for granted, okay? And the second one is that the number of planar poles is exactly the number of independent kinematic invariants. But here in this case, we saw that there are 16 planar poles, but the number of kinematic invariants is 6 choose 3 minus 6, which is 14. This means that there are two new relations, that we haven't seen in the standard case. So this is one of the new features. Now to see how number 1 also generalizes, or that is not true, we need a proper definition of the generalized Feynman diagrams. And that's where we are now. So we have done the part of tropical Grassmannians, we have generalized that, we have generalized this part, and now is the time to go from regular Feynman diagrams to what generalizes that for the case of the tropical Grassmannian 3N or for the CH5 formulation on CP2. And these are what are called collections of Feynman diagrams. So this is back the same physical question we had before. And luckily for us, mathematicians have found a generalization of metric trees for the tropical 3N Grassmannian. Moreover, generalizing the technique for evaluating Feynman diagrams that I gave you before, one finds perfect agreement with the CHY evaluation. So the best way to explain what HJJS did is to give you an example. And this goes by the name of arrangements of metric trees. So for 5 points, an arrangement of metric trees is an arrangement or a collection of 5 trees, not defined on 5 labels, but each one of them is defined only on 4 labels, where the ith tree is defined on 4 labels obtained by removing the ith label from the set 1 to 5. Well, you can see clearly here that the first tree doesn't contain the label 1, the fourth tree doesn't contain the label 4. Now, each tree has its own metric. Everything is its own, even the length of the external edges. So we denote that by saying that there is a super index 1. Now, the most important theorem in this talk is the following, is that if the following condition, meaning that the distance from B to C in the 3A is equal to the distance from A to C in the 3B and is equal to the distance from A to B in the 3C, then the completely symmetric object, thus defined, gives you a tropical Fluker vector in 3M. And the converse also holds. So this has to be the correct generalization that we need. Now let's see how we can evaluate this object. Well, if each tree was taken independently, each one has its own metric. So we could just take this product of all of them. So we could take the product of all 5 Feynman diagrams, but that would be too simple because the distances would not satisfy the conditions we mentioned before. So we have to impose that those conditions are true. And in this particular case, they are imposed by 3 delta functions that force this length to be equal to this one, the fourth to be equal to the fifth, and this equal to the sum of this and the fifth one. Now, imposing those conditions, we can evaluate this function R of t and see what happens. So we go from a 5-dimensional space to a 2-dimensional space, and the argument of the exponential simplifies very nicely to objects that we can perhaps identify with the generalized kinematic invariance that we saw before, S345 and S135, 1, 2, 3. Evaluating this very complicated integral in Mathematica gives you 1 over these functions. But now this looks suspiciously similar to what we had for 5 points before. In fact, it's not surprising because these 2 Grassmannians are dual to each other. Therefore, there must be a canonical identification between the 2 things. So we have an identification between S12 and the generalized 345 and 45 and the generalized 123. And therefore, this object is nothing but the dual version of the standard Feynman diagram that we studied before. And this actually holds for any Grassmannian G2n and Gn-2, n. Therefore, any Feynman diagram that you have ever seen has a dual version in terms of generalized Feynman diagrams. Very good. So given that we don't have much more time, I'll leave the generalization from tropical free n to tropical kn to Guevara to Alfredo's talk after the break. And instead, I'm going to jump directly to planarity. Now, why is planarity something that simplifies our lives? At tree level, each Feynman diagram is planar with respect to many different orderings. And a color decomposition is a way to separate an amplitude into manageable parts. So that's the simplification at tree level. At root level, planarity is even more significant because it allows us to have the notion of an integrand. On-shell diagrams connect to Clavic graphs and to the positive Grassmannian that led to the discovery of the amplituhedron and the connection to cluster algebras, etc. And this is a good point to mention, a good opportunity to mention the fascinating connections between the positive tropical Grassmannian, the hypersimplex, the amplituhedron, the stringy canonical forms, generalized particles, etc. that were recently found in various collaborations. And in fact, we have heard and will hear much more about this in these talks. Now, back to our story. What can we expect by restricting to the positive part of tropical Grassmannians or CH5 integrands with only products of part Taylors, or the correct notion of planarity for arrangements of trees, whatever that notion is? Well, first we have to define the notion of planarity. And for that, let me give you a definition. And we say that an arrangement of metric trees is called a planar collection of Feynman diagrams if there exists an ordering alpha such that the I3 in the collection is planar with respect to the ordering induced by removing alpha I from the order alpha. So note that this condition of planarity on collections is actually a very strong condition. So here are two examples. One is a collection that is planar for 6 points with respect to this ordering. And here is a collection that is not planar with respect to any ordering, but is also a collection of metric trees. And before we jump into planarity or diving into planarity, let me give you the evaluation of this non-planar object. So once again, imposing the compatibility of the metrics on each of one of the trees, we find a 4-dimensional space. And performing the integral that I've defined before, we get something very simple, just the product of 4 objects. If you see already from here, we see that they are intrinsically non-planar. Now, the same calculation can be done using a CH5 integrand of this form, which you can check cannot be written as a product of 2 part Taylors. So this is an intrinsically non-planar object already at what we could call the generalized tree level. Now let's go back to planarity and use the power of planarity. So back to the 5-point case that I showed you before. So this particular, why is planarity so powerful? Well, let's start with any Feynman diagram in one of the quadrants, so say this one. And now consider the degeneration when L4, the length 4, goes to 0. So we follow the path towards this point right here. And this point here corresponds to this degenerate Feynman diagram. Now, if we have planarity, there is a unique planar move, meaning that after a degeneration, there is a unique way of opening up without going back to the original object and produce a new object that is also planar. So in this particular case, after reaching the degeneration, we find a unique new Feynman diagram. And we can continue the process and go on our trip around this polygon and find all 5 Feynman diagrams via degenerations and using that the planar move is unique. Now let's do that for the planar collections of Feynman diagrams. So let's start with the same example I gave you before. This particular one has 6 parameters constrained in these 2 particular ways. So it's also a 4-dimensional object. And it has, of course, now it has 6 possible degenerations. We can take any of the 6 possible parameters to 0 and find 6 degenerate collections of Feynman diagrams. So let me take x to 0 to find this degenerate collection where we have these 2 diagrams have degenerated to this, and the other 4 diagrams just go along for the ride. Now we can open it up to produce a new collection, which is unique. And it turns out to be given by these two Feynman diagrams and the same 4 that we had before. Now, this object is supposed to be 4-dimensional. It has 4-dimensional parameters, but again, we can intersect with the unit sphere and they get something that looks much simpler, or that at least that we can draw. It turns out to be a bipyramid. So the space of these objects is a bipyramid, the interior. The boundaries correspond to the 6 possible degenerations. This particular one could correspond to this, and we pass through the boundary to reach another one of the collections. Now we can play this game many, many times with this one and start, say, with a bipyramid here and draw an edge every time we have a degeneration. So this guy has 6 edges connected to it, corresponding to degenerations, and we can keep going and going and going until we cannot produce anything else. And it turns out that we exhaust the whole space after we produce 48 configurations, after we produce 48 planar collections. In fact, in red, I have shown a Hamiltonian cycle that allows you to construct everything from this, okay? And there is, of course, a deep connection between these collections and clusters of a D4 cluster algebra from James Stock, and between the generations and mutations. Now, there are very pressing questions, or the most pressing questions are the following. Is there a physical realization of these generalized Feynman diagrams? Also, what lessons can they teach us about quantum field theory? And what is the notion of locality and unitarity? So, in the rest of the talk, I'll give you the answer to all this, but I see that we are out of time, so maybe I won't give you the answer to all of this. No, well, I'm joking. So I don't know the answer to any of these questions, but maybe I'll use a couple of minutes to tell you some results that I find amusing. So very quickly, because I'm already 1 minute over time. So I'm gonna tell you about some, as I said, a generalization that I find very interesting. So in 2013, CHY used the fact that the set of all planar poles in phi cube form a basis of the space of kinematic invariance to study the scattering equations and test the CH5 formula for the identity by drawing a partial amplitude by setting all this to 1. All planar poles, all planar kinematic invariants were set to 1. Now, if every propagator is exactly equal to 1, then each Feynman diagram contributes 1 to the amplitude. And therefore, the amplitude does nothing but count the number of planar cubic diagrams, which happens to be the n-2 Catalan number. Actually, these Catalan numbers, the usual ones, are called 2-dimensional Catalan numbers. Now, could there be, okay. Now, given that there is a 1-to-1 correspondence between planar Feynman diagrams and facets of the tropical G2N Grassmannian, then this object also counts the number of facets of this simplicial fan. Now, could there be any connection between these two, and these two? Well, the answer is yes. But in order to get there, we have to realize that for generalized Feynman diagrams and the CH5 formulas, there are more planar poles than the dimension of the space kinematic invariance. So what do we do then? We cannot just go and set everyone to 1 because they are not independent. So we have to do something else. It turns out that Nick found a solution to that by defining a height function on the hypersimplex, which assigns a particular linear combination of kinematic invariance to each vertex in the hypersimplex. Now, those are slightly more than what we need. We have n too many, but it turns out that this function exactly vanishes on n of them. So we get n choose k minus n non-vanishing functions, and they precisely provide a basis for the planar poles. Now, what to do is obvious. Well, at least something that you could try is to set all elements in Nick's planar basis to 1 and evaluate the scattering equations or the sum over generalized Feynman diagrams and see what you find. And what you find is nothing but the multidimensional Catalan numbers. So indeed, the 2 that we saw there was not an accident. It's actually something that has to do with the fact that we are doing the tropical G2N Grassmannian. And when we generalize to the positive tropical GKN, then the Catalan numbers become the k-dimensional Catalan numbers, and we get the n minus k form. All right. So, so I think I'll leave it up to here. I'll just flash some other, okay, no, this is too tempting not to tell you. Okay, just 1 minute. Okay, so one more thing is that the number of solutions that James and Song were referring to for the scattering equations have a very peculiar behavior for k greater than 2. So for k equals 2, CH5 showed that the n-3 factorial number of solutions can be derived using a soft recursion relation. And that's fairly simple. You take one particle to be soft, then the nth particle decouples. The equation for that nth particle has n-3 solutions, and the n-1 particles that you have left over, they satisfy their own scattering equations, and therefore the new number of solutions is n-3 times the number of solutions for n-2. And given that for 4 particles you get 1, then this is the solution to the recursion relations. Now you do the same thing for higher k. You start with 5 particles, k equals 3 is equal to 2 since there is a duality. For 6 particles, you solve the equation for the soft particle is 13 solutions times 2, which is this 2, gives you 26. You do it for 7 particles and k equals 3. You find the 26 from here. You solve the equations for the 7th particle soft equations, and you find 42. You get this number. Now you do it for 7 particles and k equals 4, just for fun, you say. And you find that it has to be the number for 6 and k equals 4. And this number of the soft solutions that you find to be 192. Now using the duality, this is 6, and you get this number here. Now, but wait, what's happening? This is not even interesting. It's just completely wrong. Everywhere we have been using that these two numbers are supposed to be equal due to the duality. And in this case, we find that these two numbers, which were supposed to be equal due to the duality, are not. Now, the solution to that is that there is something new that happens for k equals greater than 2, which is that even in the soft limit, we have regular and singular solutions. And so far, the story was only about the regular solutions. And once you take into account the singular solutions, order is restored, and these two numbers become the same. And the configuration of these singular solutions is fascinating, but this would be the subject of another talk. So let me end by, sorry. Yeah, no, I won't get there. So let me stop here. Thank you.
Thanks, Freddy. That was very, very interesting. Let's all applaud. And, in light of the fact that we essentially have 15 minutes until the next talk, and it's also essentially a continuation, I hope you will agree with me to just take one question for now, and then continue informally during the break, and also perhaps after Alfredo's talk, if that's fine.
Okay.
So I see, great, thanks. So let's have Nima, who was waiting already from the previous, yes. Nima, please go ahead. Yes, you were in line already from the previous talk.
Great seeing you.
Yeah.
Along the lines of the sort of what the physical significance is, or what the physical model might be, I wanted to see if you had something to say about this sort of really interesting qualitative fact about the objects you're talking about. For the G2N case, we know that factorization works by factorizing these amplitudes into the product of 2 lower amplitudes. But we know that something new is happening starting with k equals 3 and above, that when you go on a pole, the sort of facets naturally break up into, they have at least components that break up into 3 and also higher pieces. Do you have some interpretation for that from the diagrammatic point of view, or from any other point of view? If there's a physical interpretation, that seems like one of the most sort of qualitative facts to try and understand.
Yeah, indeed. So the mathematical interpretation is simple. These are the metroidal subdivisions of the hypersimplex. Now the physical interpretation is the difficult one. So I guess maybe we can discuss more about this after Alfredo's talk, where he will talk more about the as you see, the title of his talk is Generalized Locality. So maybe we can try to brainstorm after his talk.
Great, thank you.
Okay, let's thank Freddy one more time.